In this section, we're going to look at the applications of coordinate transformation in GIS. So this is an example here. So in this example, we're going to have the data in global coordinate system, and we want to transform to local coordinate system. The data that we're going to choose for this example is in here. It looks like this. So inside this file we have 71 points, and it's in GTA 94, a GTM coordinate system. It's equivalent to the global coordinate system. And if we want to convert this data into a shapefile and put inside AutoCAD, it's gonna look like this. So this is the location of the point, and this is a CSV file. We can import into pandas, and then we can show the data using pandas. Looks like this. So we can compare what the data is in pandas on the left here and data from CSV file on the right here. Okay. So what we need to do is we need to select a new original point of the new local coordinate system. Like in this figure here, we need to find the OK point, so we need to select one point representing OK. And in here, after we import pandas, we put in the location to the file. We read that CSV file in using pd.read CSV. After that, we import Numpy, and we convert pandas column to a Numpy array. Then we show the content of the pandas data frame, and we have this result. So this is a Numpy array of easting data, and this is a Numpy array of northing data. So we decided to choose the new origin of the local coordinate system is this point. So we're going to copy this, and we go to AutoCAD here, and then we draw a polyline, and we put it in here. So let's say this is here, paste it in here, enter. Okay. So let's make it a horizontal line like this first, enter. This is a new origin. We need to have the new rotation angle as well. So we choose the rotation angle is 50. So it's going to be rotate here, choose this point and put in 50. Okay. So now we can extend it up to here. Okay. So this is going to be a new local x-axis. Let's like this, just to make an arrow for the coordinate system. Okay, and we're going to copy this and do an array. This is going to be a polar. This is the center. Oh no, need to do an array. This is the object. Go to polar. We're going to choose the axis of rotation. So we're going to choose 50. So just type in 50 here. A bit weird. So we just copy this here, and we rotate it, make it easier. And we type in 90. So we have a new coordinate system here. Okay. So we know it's this angle, which is a rotation angle, is 50. 50. Yeah. So let's make the dimension bigger, for example 10. Yeah. So now make a capture and we can put it in our Jupyter notebook. So to make it in here, to have a figure in here, and also can put in here as a figure if we want to. Yeah. So basically now we have EA, E and R is synchronous and not synchronous of 70 points in the global coordinate systems, and we want to transform them to local coordinate system. We know the new origin is this. We know the rotation angle is this. Okay. So the first thing we need to do is we need to do a translation. So translation is T. So because we have the new origin, so that means the translation is going to be the coordinate of new origin. That's why we can define the translation vector T. Then we have the new PT. So if we get the first point in the data frame is this point, then after translated we will have the new coordinate of this first point is 0.0299 and 3.4328. If we check in the new coordinate system, let's see the point. So this is the first point. We're going to look for that point. Okay, so the first point is this point. So this is the first point. And this first point, if we draw like this and we draw like this, so we need to check the first point if it is the point that we are looking for. Let's check this again. Not the point right here. We paste this in here. We put it here. Okay, so exactly that point. Okay. So after we translate, that means this point now we'll have this coordinate. So in y direction it's 3.4329, which is this one, and the x direction is very small here. So if we measure the distance between here and here, you see that the distance is 0.0299, which is this one. So that is after translation we have that new coordinate value, but we also need to do the rotation as well. So to do the rotation, we need to define the rotation matrix. Because the rotation angle is -50, so we can define the phi degree is -50, then we convert it into phi radians, and then we can define the rotation matrix look like this. And then we can apply that to the input point after the translation. So this is after the translation, we have that, and after rotation we will have the new point looks like this. So this is the coordinate after rotation. And then if we go to here, we delete this, delete this, delete this. So after rotation and translation, we will have new coordinate of this point in the new coordinate system, which is 2.1 and 2.6, and here we got 2.1 and 2.6. Okay. 2.1 is in x direction, 2.6 in y direction, 2.6 and 2.1. Yeah, 2.6 and 2.1. It's correct. Then the final thing is we need to do the scaling, but in this case the scaling is 1, so the result is still 2.6 and 2.1. So that means that we test for 1 point and we use a matrix transformation, and then we have the result correct with the figure that we check here. Now we need need to combine them all using matrix notation. So to combine them all, we're going to put this in here. We put in here is a rotation matrix, and then the scaling matrix, and we put in the so P is the input and PS is the final, and then we have that result. Similar here, we gonna make it shorter and more concise. So here P is input, then do translation first. Here we do translation first, and then we do rotation. Yes, and here we do rotation, and finally we do scaling, and then we have the result. And the result is exactly 2.6 and 2.1 here. 2.6 and 2.1. So that is for one point, but now we need to apply the transformation for all 71 points. How can we do that? So in order to do that, firstly we're going to need to import it as we import the data of this CSV into a data frame here. Then we convert the easting and northing column into two Numpy array, which is E and E and N here. And then we define transform local 2D function with the inputs is in X, in Y, and translation, the rotation angle, and the scaling factor. Then we define the input value point, then we define the translation vector, the rotation angle, the rotation matrix, the scaling matrix. Then we get the output. With this output, the order of the translation is translation first, then rotation, and finally scaling. And then we got the output, and we return the output. So in order to do transformation for 71 points, we just loop through the Numpy array and add data and compute the transformation, and then add data to a new Numpy array. So here we define the input as this, as the first value. We test it, then we test it, and then we get this. After we test it, we find it's okay, then we just loop through the value in this array, and then we print it out. So after we do that, we can see that we have a new result, which is a new data frame with two new columns, which is E local and N local, which is a value of the same point but in local system after coordinate transformation. And here we can use pandas to filter to make two different data frames in RDK and PPK, and then we have the result here. So that's it. And after we do that, we can after we have the data frame, we can actually save the data frame out a CSV file if we want to. So for example, here if we have that, we're gonna try that, which is .to CSV, and then we define the output file. We say output file is let's say that we want to make the output file here called file location output, which is RTK, and make it a CSV. Yeah, and then output is PPK. So let me get RTK. We copy the path and we put this in here. Okay, then we put here is output RTK. Paste in here. We run it. After we run it, we open this file. There's nothing in there. Something wrong with it. Local. Okay, so let's see what happens. Oh, okay, here. I forget to put this in here, and then you can put in the index as false. So something wrong there. Okay, let's ignore it. Something wrong because it's open. Okay, do this again. Okay, here the path is not correct. Let's correct the path. Okay, so it's done. So the local RTK is already saved to output file RTK. I want to open that. You see that. Because the program it will have an index from the beginning here. So to fix this, I'm going to make index is false, and then check the update of this. Now we have that. Did we open using Excel? it will look like this in this cell. Okay, similar inside pandas here. Similar we can do for PPK data. Then make it PPK, and the file should be PPK. So before running, we check the file. Nothing in the file. So now we can run it, and we check the file, update it, we got it. And if we open by Excel, we should got it here. Okay. And if we check it with the data frame, exactly what we have. Pi number, local, not local, the position, type, survey, and multi-beam name. So that is an example of how we can implement coordinate transformation using matrices, rotation matrices, translation matrices, scaling matrices for a set of data points.